Example 3 is asking us to find any critical points of the following functions. We're going to go ahead and tackle the polynomial first. Remember, to find critical points, we want to be able to find the first derivative, and we want to see where the first derivative is equal to 0, and also where the first derivative happens to be undefined. So that's the task. So then starting with A, let's find the first derivative of the polynomial. F prime of x is going to be equal to 3x squared minus 12x plus 9. And then factoring 3 out, that will give us 3x squared minus 4x plus 3. And then factoring the quadratic, this will be x minus 1 as the first factor and x minus 3 as the other factor. So then this is f prime of x. So then to find critical points, I am going to be using CP for critical points. I have to see where is f prime of x equals to 0, if at all. In other words, 3 times x minus 1 times x minus 3, when will this be equal to 0? Then I just solve that equation. That implies that x minus 1 is equal to 0 or x minus 3 is equal to 0. In other words, x is equal to 1 and x is equal to 3. So then so far, as if we have found 2 critical points. Now remember, by definition, however, a critical point has to be in the domain of the function. So we have to check whether 1 and 3 is in the domain of the function. And the good news there is that yes, it is, because see, the domain of my function f consists of all real numbers from negative infinity to positive infinity. So then 1 and 3 are perfectly valid critical points. Now, we have to also consider if the other part will be, is f prime of x undefined at all? And the good news, or another good news here, is that polynomials are defined everywhere. And beautifully, they are completely smooth. They don't have any sharp corners. There are no jump discontinuities, no removable discontinuities. So then that means that I can draw a tangent line anywhere in the domain of this function. In other words, f prime of x is never undefined. That means that these are the only critical points. So as a conclusion, I'm going to say here, therefore, the critical points are going to be x equals 1 and 3. So these are the 2 critical points that I found. We will now do something very similar for part B, g function. Now, the first thing that I'll do right away is to figure out the domain of my function g. If you notice, the only issue here happens to be with x in the denominator. In the numerator, we have the cube root because of these 3 right here, and cube roots are defined everywhere. So the only issue here happens when x is equal to 0. In other words, 0 can never be part of the domain because division by 0 is undefined. So we're going to say here that the domain of g happens to be all values from negative infinity to 0, but not including 0, and then union from 0 to positive infinity, again, not including 0. Then we're going to go ahead and continue by finding the first derivative. Now this is just applying the quotient rule. I'm going to go ahead and skip that work. I will assume that by now you can handle that nicely. When we find that derivative, again using the quotient rule, we find that g prime of x is going to be equal to 6 minus x divided by 3x squared times x minus 2 to the 1/3. That becomes our derivative. So now we need to figure out when will this derivative be equal to 0? And then later on, when will that derivative be undefined? So let's do the first one first. So number 1, when will g prime of x equal 0, if at all? Because we have a fraction, the only way that a fraction can be equal to 0 is if the numerator is equal to 0. I don't want my denominator equal to 0 as well. Remember, 0 over 0 is indeterminate. That makes no sense. So just when the numerator is equal to 0. So this is true as long as 6 minus x is equal to 0, which really means that x is going to be equal to 6. Now, before I declare this a critical point, I have to make sure that 6 is in the domain of my function. So I'm going to go back to the domain over here, and I see that 6 is a valid number. It is in the domain, so I'm super happy with 6. Now I have to figure out, are there x values that will make my derivative undefined? And because that derivative has a denominator with variables, there are x values. If the denominator is equal to 0, then the derivative is going to be undefined. So the derivative will be undefined when 3x squared times x minus 2 to the 1/3 is equal to 0. And what does that mean? That means when 3x squared is equal to 0, or when x minus 2 to the 1/3 is equal to 0. So now we're just going to go ahead and solve each equation separately. So then when x is equal to 0 in this case, and here, remember the way to get rid of this exponent is by cubing, doing the opposite of the 1/3. So then that means when x minus 2 is equal to 0, when x is equal to 2. Now, however, I want you to go back and look at the two possible candidates for critical points. Critical points have to be in the domain of the function. 0, if you remember, going back over here, was excluded from the domain. So 0 will not be a valid critical point, out. And then what happens with 2? 2 is perfectly valid. So that means that we found 2 critical points. Conclusion, we're going to say, therefore, the critical points are x equals 2 and 6. These are the 2 critical points. Example 4 is asking us to find the absolute maximum value and the absolute minimum value of each of the following functions, f of x and g of x. In order to do this problem efficiently and also very quickly, we want to be able to use the extreme value theorem, the EVT. The extreme value theorem, if you remember, said that if a function is continuous in a closed interval, AB, then we know for sure that it has an absolute max and an absolute min. But on top of that, the theorem says that this absolute extrema happens at the critical points or at the end points. So again, the critical points or the end points. So that's where we have to search for these values. Notice that in part A, I have a polynomial. You may already notice also that this polynomial is the same polynomial that we had in the last example, in example 3. I am recycling the same functions because we already found the critical points and I don't want to have to do all that work again if I choose new functions. So I'm using the same functions as in example 3. That means, if you remember, that the critical points that we found there were 1 and 3. So all that I have to do now in order to apply the intermediate value theorem is to consider the y values at these points. That means at the critical points and the end points. Now, the critical points of the first polynomial were 1 and 3. You can see them right here. However, only 1 is in the closed interval 0 to 2. So then that means that 3 will not be considered here because 3 is not in the closed interval. So we will then compute f of 1, and then we will exclude 3 again because 3 is not in the closed interval. And then we're going to go ahead and compute f of 0 because 0 is the left endpoint, and then f of 2 because 2 is the right endpoint. So the the extreme value theorem says that one of these is going to be the absolute maximum and one of these is going to be the absolute minimum. Again, because that's going to happen at the critical points or at the end points. Again, we excluded 3 because 3 is not in the closed interval. So now we're just going to go ahead, take 1, and plug 1 into every x that we have in that function. For example, 1 minus 6 plus 9 plus 2, that's going to give us 6. Same thing with 0, that will just give us 2. And same thing with x equals 2. When we plug in x equals 2, we get 4. So then from here, we see that 6 is the highest y value. That means that this is the absolute maximum value. And that happens exactly when x is equal to 1. And then we see that 2 is the smallest y value. So this is the absolute minimum value. And that happens when x is equal to 0. So then if you notice now that x equals 1, exactly here, x equals 1 is a critical point. So we achieve one of the absolute extrema at a critical point. And then x equals 0 is an endpoint. So the other absolute extrema is achieved at one of the endpoints. So whenever we have a closed interval and the function is continuous in a closed interval, the way that we find for absolute extrema is by calculating the critical points and then evaluating the y values at the critical points that lie in the closed interval AB and also at the endpoints. Let's go ahead and pretty much repeat the process with the other function, with g of x. So now for g of x, the closed interval happens to be 1 and 10. And if you remember again, the critical points are 2 and 6. Now both 2 and 6 lie in the interval from 1 to 10. So that means that we have to go ahead and consider g of 2. We will consider or compute g of 6. And then g at the endpoints, g of 1 and g of 10. Plugging this into the function, we get 0 for g of 2. For g of 6, we actually get an approximation of about 0.42. G of 1 is equal to 1, and g of 10 is about 0.4. So now we can see that 0 is the smallest y value. So this becomes the absolute minimum. And that happens precisely when x is equal to 2. And if you notice nicely that x equals 2 is precisely a critical point. So that's where we have one of the absolute extrema. Then we look for the the largest y value that we have. And the largest y value happens to be 1. So then that means that 1 is the absolute maximum. And that happens precisely when x is equal to 1. And x equals 1 is not a critical point. X equals 1 is the left endpoint. So the other absolute extrema happens at the left endpoint. So this is exactly how we put the extreme value theorem in practice. Given a continuous function in a closed interval AB, we find the critical points and then we evaluate the function, the y values at the critical points and the endpoints. We look at all of the values and we pick the largest y value. That's going to be the absolute maximum. The lowest y value is the absolute minimum. You do have to be careful that when you look at the critical points, though, you only choose the critical points that lie in the closed interval AB.